I get about that far. And
well, welcome back to our class. I just wanted to take a couple of seconds or a couple of minutes and talk to you about the Project Not licenses. So today you should have received an email from me that had your license information into it. All it is, with the exception, I got to redo yours.
okay.
Yeah. So all that you need, so you have the website is posted in there, and it's mrooms.net, and that's in your email. And then your username is just your first name dot last name, and then the password is change me. So you'll go in and change and make your own password for that. So that is how that works. For those of you that are in Adobe, everybody that signed up for them got them, except for a couple already had licenses that were issued previously. So I've already emailed you about that. Are there any questions with that? I think in the email I gave you until March 5th. I wish I would. And reissue them to cohort number 2. After both cohorts are finished, I'll gather all the licenses back in. I'll send out an email to all of you, and then I'll issue to them to any of you that want the extra practice on a first-come, first-served basis. Does that make sense? So if you have any questions, or if there's any issues or anything about logging in, you're welcome to email me, and I will contact Ohio State University is the one that we're working through on this project. She's pretty quick to work with me. The beginning of the week is a little bit easier because as things, get bogged down during the week, the latter part of the week tends to get pushed off till the beginning of the next week. So if you have issues, I would go home, and if you have just a couple of minutes just to go in and log in tonight to get in to look at them and make sure that everything works okay. And if you have issues, please email me, and I'll get on that first thing in the morning and email her and see what we can do about that. Any questions here about that? Yes?
So is it just practice stuff, or is it classes, or what is it?
So their practice, the question was, what is Project Not? Project Not is our online modules. Have you ever done like Khan Academy? Okay, so Khan Academy, they'll just put like a practice problem up there on the board, and you'll see a little hand, and it will kind of go through and work you through it. So you'll get a series of modules, and you want to go to the middle school math, because that is the Praxis test that you're taking, is the middle school math. So, and you can just work through them, you can stop them, you can replay them. So it's just extra practice and extra help on the definitions and things. Do you guys have anything else to say about them? I know you guys have been on them.
I would say the modules are good, but don't get overwhelmed with the practice test. The practice test is, I don't know, what's a good word for the practice test?
According to what is, and I know, according to what is in the ETS guide, the study guide, and the topics that we passed out at the very beginning, that practice test goes above and beyond what is in the study guide. And so that's why we don't want you to get super concerned, is because there are some calculus topics, but according to the ETS study guide, those are concepts you would not be tested on the middle level Praxis test.
Yes. And in addition to that, not even just the topics, but also, some of the questions are asked in a way that it almost feels like it's a trick. They're trying to trick you, which in looking at the practice test or practice questions on the ETS website, they seem more straightforward, to the point, not, testing your knowledge, not testing if you're paying close attention. So, I wouldn't.
So don't get hooked up on the practice test,
yeah,
but go through the modules and get some extra practice.
And if you want to try the practice test, that's great. Just don't panic about it. So, yeah.
Any other questions concerning Project Not? Yes.
So how do you access it?
You'll go
It's on the
to,
website?
yeah, you'll go to the website mnet.mrims.net. Tell me your name.
Christy Gordon.
Christy Gordon. For some reason, I don't have you on the list. Were you here last week?
Yeah.
Okay. Let me talk to you afterwards. Okay. Okay. Any other questions? Yes.
I have the same concern. So, Jackson.
You received an email today from me.
Oh, I did. Okay.
Yeah. So the emails went out today from me, giving you your login information and the website. Were there any questions in Adobe?
Not right now.
Okay. Okay. If there are no other questions, if you have questions, you can feel free to come back and ask me, and I'll stay after the class too if there are any other questions that I can help with. Okay. Thanks, Al.
All right. Well, thank you. Okay. Let's jump into some math, because we can all tell how excited everyone in here is. All right, so last time we left off, and we had a request that somebody wanted us to do number 42 on, I gotta stop looking at that when I have my hand on it. So number 42 on the sheets that we handed out last time. And I thought, what a great place for us to start out. We'll hit this real quick, and then we're going to jump into some probability, which, again, very fun topic. All right, so number 42, it says the ratio of votes for Robert to votes for Jessica. So the ratio, I guess I better do a capital, for Robert to Jessica is 4 to 1. Then it says 212 people voted for Robert. So if I were to set up another ratio right here, what side of that ratio is the 212 going to go on? Okay, it's going to go on the left. Why?
4 is.
Okay, good. Yeah, because the 4 belongs to Robert, right? It's the ratio of 4 to 1, Robert to Jessica. We've got to be very consistent. When we're dealing with ratios and proportions, we want to make sure that we're putting the right value in the right spot. And so we're very consistent. All of these values on the left side are Robert's values. So Robert received 212 votes. How many people voted for Jessica? So that's our X. All right. Now, we've got 2 ratios here. What's it called when you compare 2 ratios? Okay, when you equate 2 ratios, it's a proportion. Very good. So there's some more vocabulary for us. Now, I can write it like this. Or I can write it 4 to 1, or 4 is to 1 as 212 is to X. I can write it that way. Or I can write it like that. Okay, so there's my proportion. I've got 4 over 1 equals 212 over X. Now again, we want to make sure we're very specific about where our values are going. And that we can justify why we put it where. Well, I've got Robert compared to Jessica. Robert compared to Jessica. All right. Now, I know we all tell we tell our students that when you have a ratio or a proportion, to solve it, you cross multiply and then simplify it, right? Why do you do that?
find out what X is.
Yeah, you're looking to find out what X is, but why do we say we cross multiply? And that's one of the things that really, it's not a major secret, it's not really complicated. All we're doing is, when we cross multiply, we're getting rid of our fractions. That's it. And let me show you, without cross multiplying, I'll show you how it's done. And then we'll cross multiply and just show you. But this is where the cross multiply comes from. I've got an X on the bottom. How do I, it's by fraction here. How do I get rid of it on the bottom? What can I multiply this side by? X, or X over 1, right? Well, if I multiply this side of my equation by X, I've got to multiply this side of my equation by X, or X over 1, right? So, X over 1 times 212 over X. Well, what's X divided by X? 1. Okay, so X divided by X is 1. That leaves me with 212 over 1, right? Which is really just 212, right? Oh, I gotta scoot it up. There we go. So we can do 212 over 1. Let's leave it like that, just so we can be consistent and show. Now then, I've got over on this side, I've got 4 times X over 1, which would just give me 4X over 1. Now, this one works out pretty good because we've got it over 1, but what if that was like over a 3? Well, then I could multiply both sides by 3 over 1, and it would get rid of that side. So that's really, that's where cross multiplying comes from. All we're doing is getting rid of the fraction. It's not a huge secret. It's not, people didn't come up with this. Monks in a quiet chamber came up with, ooh, I've got a way to solve proportions. That's just all we're doing is getting rid of the fraction. Okay, so 4x over 1 equals 212 over 1. Again, this is just 4x equals 212 because anything divided by 1 is itself, right? How do I solve for x? Divide both sides by 4. So my x is going to equal, what's 212 divided by 4?
53.
Okay. So let's see if we've answered the question. The question was, how many people voted for Jessica? Well, if x is equal to 53, let's go back up to the top. So x is equal to 53. Well, we've got comparing Robert to Jessica, Robert to Jessica, Robert to Jessica. How many total votes did Jessica get? Jessica got 53. So there's our answer. Any questions on that? Okay, so the cross multiply, you guys, the cross multiply, let's just look at this real quick. 4 over 1 is equal to 212 over x. We cross multiply, we get 4 times x is equal to 1 times 212, and then we solve from there. But again, really cross multiplying, all we're doing is just getting rid of the fraction. All right. Any questions before I move on? Fantastic. Okay.
We do have a question from Adobe from
Yes.
just the last time's homework. Are you taking those questions?
You know what? Yeah. Let's take the question. Let me write them down. Which ones we want to look at. But we're going to talk about probability, and then we'll come back to last time's homework. So absolutely.
So we're changing things up a little bit this time.
Yes. So what are the questions they want to see?
Just want to know if you show factoring a trinomial, just an average question, how to do that.
Oh, yes. I would love to do that. All right. What was it?
As I say, those ones are mine.
Those ones are yours? Okay. Well, and absolutely. I will let Chad tell you. But I love
Yeah, I
that
can
one.
get one. Oh, I'm sorry.
Okay. So let's start with a fundamental counting principle. Okay. So basically this says that when two or more choices must be made together, we can use the fundamental counting principle. And it says if one item can be selected m ways, and for each way a second item can be selected n ways, then the two items can be selected m times n different ways. And this goes back to, remember when we were talking about the outfits? When we were, okay, let's talk about my daughter's closet. Okay? Let's jump right into a big nasty. Let's say that my daughter, who just got married last Saturday, we packed up her closet. Oh my gosh, she had like 5 boxes of clothes. And this isn't counting the stuff she had already packed up. I don't know how she collected all this. Okay, so let's look at her closet. Let's say she has, and I'm gonna downplay this a little bit. Let's say she has 10 shirts. And let's say that she has 8 pair of pants. And she's got lots more than that.
It's not showing.
It's not showing? Okay, there we go. There we go. Thank you. Okay, so 10 shirts, 8 pair of pants. How many different outfits can she wear with that example? Okay, 80. And how did we come up with it? The 10 times 8. Okay, so we took 10 times 8. It gave us 80 possible outfits, right? I'm going to do the times. There we go. If we had fewer, it would be easier for us to draw a picture. So I'm going to jump to an example that's a little bit fewer. Let's say that she has 3 pair of shoes, which we all know is a lie. She's got lots more than that. And 4 pair of socks. All right. So this one, let's kind of draw this out and see. So the 3 pair of shoes, let's say she's got pair number 1, pair number 2, and pair number 3. She could combine pair number 1 with socks 1, 2, 3, or 4. Excuse me. Right? She could do the same for pair number 2. And she could do the same for pair number 3. So what we've done is we've said we've got the 3 pair of shoes, and for every pair of shoes we've got 4 choices to go along with it. So we can take that 3 times 4 and it'll give us 12, right? Can we get even more complicated and say that she's got 2 belts? It looked like a 2 to me, but not up on the screen. Sorry. So she's got 2 belts. Well, then we can say she's going to take belt 1 or belt 2 there, 1 or 2 there, and so on. So then we say for every pair of shoes, she has 4 options for the socks. And for every pair of socks, she's got 2 options of belt, right? So that would be 4 times 3 times 2. So what is it? How many options would she have?
24.
24. Okay. So that is the fundamental counting principle. Okay. Let's look at number 1. Okay, a car model comes with the following choices. Ooh, we love new cars. This is exciting, right? So there's 9 colors. 9 colors. It comes with or without AC. So we've got 2 choices when it comes to AC, right? With or without. We've got with or without sunroof. 2 choices for the sunroof. We've got with or without automatic transmission. So 2 choices for automatic transmission. With or without a spoiler. And my second oldest daughter would say there is no choice there. You're getting the spoiler. But we'll say with or without the spoiler. And with or without anti-lock brakes. And then it says, in how many ways can the car be ordered? Okay, so again, fundamental counting principle tells us that when we're faced with options, we got 9 different colors. For every color we can choose AC or not. For every choice of AC or not, we can choose whether it's got the sunroof or not, automatic transmission or not, spoiler or not, and anti-lock brakes or not. So we'll take 9 times 2 times 2 times 2 times 2 times 2. And what would that equal? How many choices do we have? 288. And that's a lot to think about when you're buying a new car. So just go with like that throws 9 of that brings it way down, right? What if there is only 1 choice in color? Then how many choices do we have?
32.
How many?
32.
32. 2 times 2 times 2 times 2 times 2 is 32. So if you take one of those choices out, man, it goes way down. All right. Questions on the fundamental counting principle? All right. The next thing we want to look at is going to be independent and dependent events. So, before we look at how we address these, let's talk about what independent and dependent means. And some situations that that would fall into. So if I'm going to flip a coin, and I flip a coin 5 times, is my second coin flip affected by my first coin flip? Or is it independent from that? It's independent, right? So it's not relying on what my choice was or what my outcome was that time before. So those are independent events. If I pick something out of a bag, and let's say I've got 4 red marbles and 5 red marbles in a bag. I reach in and I pull out a red marble. I set it down. It's going to roll off the table, but that's okay. We'll come back to it later. Now, I reach in again and I pull out another marble. Are those two events independent or dependent on each other? Dependent. Why? Okay, good. Because I have now affected what the probability is of getting that next one. I've taken something out and changed the odds. I've changed how we're going to look at this again. So let's say, oh boy, okay, let's say that I've got a bag, and in that bag I have 3 blue marbles and 3 red marbles. I pull out a red marble with my first. Okay, I reach in, I pull out a red marble with my first try. What is the probability that I would pull out that red marble in that first time, first try?
How many blue marbles you got?
Okay, so I have 3 red and 3 blue. So, again, the probability is the preferred or desired outcome over the total possibilities. So how many total possibilities did we have? 6, right? We had 6 marbles in there. How many of those were the desired color? 3. So my probability is 3 over 6, or 1/2, right? Half of the time, 50%, I'm going to get that red marble, right? Okay, so I pull that red marble out, I set it down. Now, what's the probability that I reach in and I grab a red marble? Two out of 5. Desired over total. Okay? There are 2 red marbles left, and there's 5 total marbles in there. So those 2 acts, that's dependent. Okay? Because I didn't place it back in. Now if I had 3 red and 3 blue, I reached in and I grabbed a marble, what's the probability that it's blue? Okay, 3 blue, 3 red. So it is 3/6, which is 1/2, which is 50%, right? Okay, so I pull that out. Now I put it back in. And I choose again. Independent or dependent? Independent. Okay, so questions on that? Very good. All right, so to find the probability of 2 independent events, both occurring, multiply the probability of the first event by the probability of the second event. So if I pull a marble out, let's do this. So we've got 3 blue and 3 red. So I'm going to pull one out. What is the probability if after each pull I put it back in, I replace it? Okay. So first of all, if I do that, what do I know instantly? Is that independent or dependent? If I'm pulling the marbles and then replacing after the pull. They're independent. Okay. So if you're replacing, if you're not changing what you're looking at, if you're not changing the probability, then that's an independent event. So we can use this. So I want to know what is the probability that I will choose 1 blue marble and 1 red marble. Okay? So I reach in, I pull it out. What's the probability that I pull out a blue marble? Okay, 1/2. Now, oh yeah, we could say 3/6, we could say 1/2, we could say 50%, however you guys want to do it. I'm going to go with 1/2. They're all the same thing, right? Now I put that marble back in, and what is the probability that, I said that we pull out 1 blue and 1 red, right? So then what's the probability that I pull out the red? Okay, so the probability that those 2 events happen is 1/2 times 1/2, which is 1/4. Okay? Questions on that? All right. Now, the probability of two dependent events. Okay, so again, the dependent event that we talked about is if I pull a marble out and I set it aside and then I reach in and I pull another, right? Or a dependent event would be if I choose 3 cards at random from a deck of cards without replacing them back in there. I'm just going to choose 3 cards, boom, boom, boom. Or, yeah, we'll stop there. We'll stop there. We'll get to that in a minute. So these are dependent events, okay? Now, the probability of 2 dependent events, both occurring, we multiply the probability of the first one and the probability of B after A occurs, or the second one after that first one occurs. So let's look at that. So again, we've got the 3 red marbles and 3 blue marbles. What is the probability that I pull out 1 red and 1 blue marble? Okay, so I want the probability of 1 red and 1 blue. Okay. All right. So if I'm not replacing those marbles, what kind of event is this? This is a dependent event. Okay. So we're going to look at, first of all, I reach in and I pull out a red. What's the probability that I pulled that red out? Okay, so this means that I'm going to have 1/2 times, I set that red down and I reach in and I pull out a blue. What's the probability I pull out a blue? 3/5. Okay, questions? You see that? Okay, so 1/2 times 3/5. 1 times 3 is 3. 2 times 5 is 10. So the probability is 3/10. All right. So let's work a few problems. Okay. Let's look at a few from the fundamental counting principle. So go ahead with your table partner. Look at number 2 and 3. Yes.
I'm so sorry to interrupt as you're moving forward.
Oh no, that's fine.
There's a question that just came in that says she still can't explain to her class where did you get the 1/2. I need it broken down more, just on that last problem.
Oh, okay, okay. So I'll tell you what. Those of you who need this, go ahead and pay attention. Those of you who don't, look at problems 2 and 3 on the fundamental counting principle. So, the last one, we had 3 red and 3 blue, and we've got them all in that bag. And so we are reaching into the bag, and we're looking at what is the probability that I'm going to grab a red. So probability is the desired result over the total number. Okay, so how many desired marbles are in there? Well, we're looking for red, so there's 3 that are red. And then we want to look at how many total marbles are in that bag. So 3 plus 3, 3 red and 3 blue, gives us 6. So then we just simplify that down, and that gives us the 1/2. Is that making sense?
Thank you, that is huge.
Fantastic. Good, good. Oh, and you know what? I did not repeat the question. So this is a little late, but in Adobe Land, the question was, how did we come up with the 1/2 in that last problem?
I just zoom over. Oh, yeah. Oh, you did it that way, huh? I just saw there's 8 for each, 4. So, for each. So we've got the options. So each option is 4 options. 4 8 times 4 is 32. So I was thinking about loans. 2 options. Each one of those options. Oh, so you're just saying, okay, 4 is 4 is 4. 8 times 4. Yeah. 8 power. These are all the same ones. They all have the same. And on this one, since they put it at 0, that's the digit. Then that's a total of 10 digits. So you go 1, 2, 5, 6, 7, 8, 9. So yeah, like 10, and each one of these is coming one of 10, 10. So there's 9. So you 10 to the 9th power. Oh, you're thinking.
Okay.
Oh, really?
Who needs more time? You guys ready to move on and go over those questions? All right. So we'll give about 5 more seconds. 4, 3, 2, 1. Eyes on me. All right. So let's look at number 2. Number 2 says that you are about to take an 8-question multiple choice test. So there are 8 questions. Each question has 4 possible answers. Okay. How many ways can you answer the test if you leave an answer for each question? So, what do we do?
8 times 4.
8 times 4, which is? 32. Very good. Any questions on number 2? You feel okay about that one? Okay. Did you have a question, Steve, or you?
Well, we were discussing between ourselves. I think we're okay.
Think you're good? Okay, okay. Okay, so number 3, a social security number contains 9 digits, such as 000000000. How many different social security numbers can be formed using any numerals from 0 to 9? So, first of all, how many numbers are there from 0 to 9?
10.
10, right? So we've got 10 choices for that spot, 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 and that spot. How many spots do we have?
7.
Okay, so we have 9 slots. So we have 10 times 10 times 10,
Oh, you nailed that.
right? Man. Okay. So what is our answer? Do I want to do the answer? I do. Okay. All right. So, moving right ahead.
How do you get that as your social security number?
You get that as your social security number, the 000, that is mine.
Oops.
Okay, so let's look at the probability independent and dependent. So we're going to determine whether the events are independent or dependent. Okay? All right. So, number one, selecting a marble and then choosing a second marble without replacing the first marble. Independent or dependent? Okay, dependent. Very good. Are there any questions on why that's dependent? That's the example I used earlier, so hopefully we've got that. Number two, rolling a number cube and spinning a spinner. Independent. Okay?
So we're going to go ahead and change gears, and we're going to look at the questions we had on our homework from last week. So we're going to start with quadratics, polynomials. When we have a trinomial, and let me find the marker. How do you have the marker? Yeah. I won't catch it.
Pages 32.
Alright. So when we're talking about factoring, let's go ahead and look at like x squared plus 9x. By the way, I'm looking on our homework. I'm looking on the very first page. It's problem number 8 on that first page. So I've got x squared plus 9x minus 22 equals 0. And we need to solve this by factoring. Oops, let's pull it down. Okay, so we're gonna keep that problem there, and I'm gonna show you using some variables for a moment something, and then we're gonna go back to this problem. We're gonna start with a basic x plus a times x plus b. If we were multiplying these together, how would we multiply them together? FOIL. A lot of people have referred to FOIL. FOIL is basically a fancy way to simply remember the distributive property, because that's all we're really doing here, is the distributive property. We are taking this variable x and multiplying it by everything over here in the parentheses. So we have x times x plus b. Then we're taking a and multiplying it by everything over here. So we have plus a times x plus b. Or we have the first, outsides, insides, and last, which is FOIL. So FOIL is basically a shortcut for the distributive property when we're doing this. Okay, so now what we have, I'm going to combine these together. You notice how there's an x in both of those? I'm going to rewrite it, and if you'll bear with me here, I'm going to rewrite it. I'm going to do a plus b or b plus a. It's the same. So when we multiply two binomials together, we end up with this. Now, why is this unique? Well, let's take a look right here. A times b, we multiply them together. A plus b, that middle term is added together. So when we're told, back to this problem right here, The way that we find the factors is we're looking for two things that multiply to be this last number and add to be the middle one. And we can see that that's true because right here we were looking for two things that multiplied. Notice that they're multiplied on the end, yet added in the middle. Okay? So that's why we can do what we're going to do. So I'm going to erase this. We're going to go back to our problem. We're looking for two things that multiply to be a negative 22. I'm going to take that sign with it. So I'm looking at negative 22. Well, what are my factors of 22? 11 and 2. So either the 2 can be negative and the 11 positive, or the 2 can be positive and the 11 negative. Now remember, I want two things that multiply to be a negative 22, yet turn around and add to be a positive 9. So which one of these is going to add to give me a positive 9? The first one. So those are what I need. The way that I write that then is I write it as x minus 2 and x plus 11. So I factored it. But I'm not done with this particular problem because if you'll notice, it didn't want me to just factor, it wanted me to solve it for 0. So I'm going to go ahead and change this back into an equation so that now we can solve this for 0. Now if you'll notice that we're multiplying these two things, what is the only way I can multiply and yet get 0 as my answer? One of them have to be 0, meaning either x minus 2 equals 0 or x plus 11 has to be 0. Notice I now have two equations that I can solve to find the answer for. X is either a positive 2 or x is a negative 11. So that's my two answers there. Now, if I want to check my answer to see if it's correct, if I substitute a positive 2 in place of this x here, it should equal 0. If I substitute in a negative 11 up here, it should equal 0. So that's a way I can check my work to see if I've done it correctly. So that's how you solve by factoring. So let's go ahead and look at another one. If you look at the very next problem, number 9, we have x squared minus 81 equals 0. Now you'll notice this looks a little different than what we just had before. The reason why it looks a little different is because we're missing that middle term there. I'm going to go ahead and put that middle term in so we can remember it. Now I put that middle term in by putting in 0x. Because what I want to point out to you, and you may have actually recognized this as being a special one. There's a couple special ones that you start doing these over and over again, you start noticing patterns. This is one of those patterns. In fact, it has a name, it's difference of perfect squares. What we're looking for are two things that multiply to be a negative 81. Now that negative tells me one has to be positive and one has to be negative. Yet, they're going to turn around and add to be 0. What's the only way they can multiply yet turn around and add to be 0? They have to be the same number, but one positive and one negative. So what I'm looking at here is a negative 9 and a 9 are my two factors. So I've got x minus 9 times x plus 9. Set that equal to 0. And then again, I do the exact same thing I just did before. If this product equals 0, then either x minus 9 is 0 or x plus 9 is 0. I need to solve those. So my answers here would be positive 9 and negative 9. Okay? So I'll let you work number 10 on your own. But I want you to flip to the next page because then we get a little more complicated. And what happens here is you'll notice, let me write the problem down. I'm looking at number Let's look at number 16. I have f of x equals x cubed plus x squared minus x minus 1. Okay, what do you notice is different between this one and the one we just saw? Has a cube. Also has 4 terms instead of 3 terms. Okay, so we need to figure out a way to factor. The very first thing that you should look at when you have something like this is look to see if there's a common factor you could pull out of every problem. Let's see if there's an x or a common number in all of those that we can pull out. We see that we don't have anything common here. So what we're going to do is we're going to do, if you remember back and look in your notes when you wrote it down, the distributive property, when we multiply this out with the distributive property, we ended up with a number times a parenthesis plus another number times a parenthesis. We're going to group it kind of like that. We're going to group these first 2 together, and we're going to group the second 2 together. Sorry, I don't want to write it that way or else it'll look like it's multiplied. We have to be really careful in our notation, or as we've seen previous weeks, I make mistakes. So I'm going to group the first 2 together. So I'm going to group x cubed plus x squared, and I'm going to add negative x minus 1 and group those together. So what I want to do is I want to look at each of these groups and see if there's something common I can pull out here. Is there something common I can factor out of this first parenthesis? X squared. So I'm going to pull out an x squared, and I'm left with x squared times what would give me x cubed? X. And x squared times what would give me x squared? 1. So it factors to be x squared times x plus 1. But I'm not done yet. I've got this over here. Now that looks vaguely similar. What if I factored out a negative? See how both of those are negative? So I'm going to factor out a negative 1. When I factor out a negative 1, I get x and plus 1 here. Now, this was done very intentional because these are both exactly the same. I'm going to use the opposite of the distributive property, basically. Because this would be saying x squared times this parenthesis and minus 1 times that parenthesis. So I just factored it. This is called factor by grouping. You group them together, pull out common factors, and then as long as you can get the exact same common factor out at the end, you can put these 2 together in the parenthesis. Because notice if I were to use the distributive property right now, I'd have x squared times this parenthesis, which is right here, and minus 1 times this parenthesis, which is right here. Now, I'm not quite done. I need to, it actually says to solve it, not just to factor it. So to solve it, I need to set this equal to 0. I can actually factor it a little bit more. And some of you may recognize that. And if you recognize where it can still factor, please factor it further. Those of you that don't recognize where it can factor, that's okay. We can still solve this because I just need to set x squared minus 1 equal to 0. And x plus 1 equal to 0. Well, here's pretty easy. I know the answer is negative 1 there. This one's a little bit more complicated. If I add 1 to both sides, I get x squared equals 1. Now, how would I solve this? Take the square root. But now here's where we have to remember, anytime we physically draw the square root symbol, we need to take into consideration both the positive and the negative side of things. So the answer here is x could either be a negative 1 or a positive 1. And then we have x could be a negative 1 right there also. So notice that there's actually 3 answers. But I'm only going to write it down as negative 1 and 1. I don't need to write the repeated root. I don't need to write the repeated numbers. Okay? Now, it's interesting that we have 3 answers here, because if you notice, it was a cube to begin with. So when you have the highest power, that's called the degree. You want to look for, that tells you how many answers you should expect to be able to find. So when we're dealing with the squareds, the polynomials, the quadratics, where the highest power is a 2, how many answers do we expect to find? 2. And it actually comes back to the graph. When we're dealing with squares, the graph is going to have a U shape. The answers occur where they cross the axis, the x-axis. Those are our solutions. So a polynomial can cross in, a quadratic can cross in 2 places. Or a quadratic could just touch. That's when we would see the same number twice, like we did on the previous problem we had worked, problem number 9. We were to graph x squared minus 81. It would touch the axis there. Or it could happen that it's way above or way below and it never touches. That's when we see our imaginary numbers come in, when there's no real solutions. So one thing you can do is, because you have access to a graphing calculator when you're solving these, you can actually graph it and look for the solutions where they cross. So that's another option. Okay, let's go ahead and look at number 15 quickly. So negative 4x cubed, f of x equals f of x equals negative 4x cubed plus 64x squared minus 220x. So your first instinct after seeing what we just did may be to want to group them together. But if you look very carefully, what do you notice is in every single one of these? There's an x in every single one of those. It also appears that there's a factor of 4 in every one of those. Now, because this is a negative, you don't have to do this, but because this leading coefficient here is a negative, I'm going to also just pull out a negative. So I'm going to pull out a negative 4x, and let's see what we have left over. Negative 4x times what would give me negative 4x cubed? X squared. Negative 4x times what would give me 64x squared? I'm going to need a negative 16x. And the negative, because negative times negative is going to give me my positive. Here I see my answer is already negative, so I know I don't need another negative. But 4x, negative 4x times what would give me a negative 220x? Okay. All right. I can see that I have an x squared here. I'm not quite factored all the way. Let's continue to factor a little more. We've got a negative 4x out front. Don't want to forget about it. Let's look at the factors of 55. What are the factors of 55? I've got 5 and 11 and, yeah, you're going, wait a second, it's only 5 and 11. What about if I had negative 5 and negative 11? Does negative times negative 5 times negative 11 give me a positive 55? It does. Which one of these is going to add to give me that negative 16x? Sorry, let me scoot that down. Which one of those is going to add to give me a negative 16? Right, so I've got x minus 5 times x minus 11. Now again, because I want to solve this, I'm going to set it equal to 0. Notice I have 3 that I'm going to set equal to 0 now. I've got a negative 4x equals 0, x minus 5 equals 0, and x minus 11 equals 0. Meaning my answers here, let's do this one. My answer here would be x equals 5, x equals 11. What does my answer need to be here? 0. So my answers are 0, 5, and 11. Those are where the zeros of the function occur. So that is the factoring of polynomials and the factoring of the more complicated factoring and solving. Also on this, there were some questions that came from the square roots. Let's look quickly at number 7 on that first sheet. And 7 said 10. Then it has a ginormous square root symbol, 36 over 64. And I don't think I did an adequate job last time describing what happens here. What you want to know is that the square root or the roots, if I have the square root of a fraction, I actually can simply take the square root of the top over the square root of the bottom. They're the same, so I can break it up. And the properties of exponents are what allow me to be able to do that. So here, this is the same thing as saying 10 times the square root of 36 over the square root of 64. Now, if we're lucky, we can take the square root of both of those nicely. So the square root of 36 is 6, because it's 6 times 6. And the square root of 64 is 8. And I still have that 10 times on the outside. So it's not 10 and 6/8. It's actually 10 times 6/8. So I need to change both of those to fractions so I can multiply them. And I end up with 60 over 8, which will reduce. Now, I'm going to give you a hint about reducing that may help or may hopefully not cause any confusion. But I find it really helpful. When I've got a product written like this, 2 fractions multiplied together, this is the same thing as saying 2 times 5, because that's 10, and 3 times 2, that's 6, and that's all over 1 times 2 times 2 times 2, which is 8. I broke it down to its prime factors. Now what you notice here is I've got some of the same factors in the numerator as I do in the denominator. When I have that, they don't really cancel each other out, but they divide off to be 1. So 2 divided by 2 is going to be 1. So I'm going to cross them off knowing that they divided to be 1. I've got another one that's going to divide to be 1, and I'm left with 5 times 3, or 15, over 2. Now I'll be honest with you, when I'm doing these problems, I don't break them down to the prime factors. I'm going to take you back up to that problem I just had. I look at it and I say, oh look, I've got an 8 and a 10. They both have a 2 in them. 2 can go into 10, that leaves 5. 2 can go into 8, that leaves 4. Oh wait, I got a 6 and a 4. They both have a factor of 2 in them. 2 goes into 6 3. 2 goes into 4 twice. And I'm left with, in the numerator, 5 times 3, or 15. And then in the denominator, 1 times 2, which is 2. Did I make a mistake? Oh, 7 and 1/2. I thought you said something was wrong. We're jumping now. Okay, so that's another way to reduce if you want to speed up your reducing a little bit. Okay? So that's number 7 with the radicals, and I wanted to expand on those radicals a little bit. In that large packet that you were given, there's a sheet that was labeled Simplifying Radical Expressions. And I just wanted to pick a couple out of there just to make sure we really had that down. Let's go ahead and look at problem number 27 from that one. Problem number 27 said 3, then it had the square root symbol, 16x to the 4th, y to the 4th, z. Now, if you remember from, thank you, if you remember from last week, we had one where we had to find 4 of the same in order to be able to pull one out. Notice there's not a little tiny number right here. That indicates this is a square root. Square roots mean we only need 2. So what we're looking for is it's nice to break everything down. If you remember the big box that Hal had done last week where he broke everything down into. So if we were to take this down and dump it into this box and break it down, we're only going to look at the stuff under the, right here. We're not going to look at the number out front. The prime factorization of 16 is going to be 2 times 2 times 2 times 2. X to the 4th would simply be x minus, or times 4 times. Same thing with y to the 4th. And then I've got my z. Now because this is a square root, I need 2 of the exact same factor to be able to pull one out. So I've got 2 2's, these group together. When they group together, what comes out is 1 2. These 2 2's group together, what comes out is another 2. Now what's nice is everything that we pull out is being multiplied together. What's that? Okay. The x's, I have 2 x's. They're going to group together, allow me to pull 1 x out. Notice everything's being multiplied as I pull it out. I have another group of x's. I have another group of y's. Another group of y's. And am I able to pull that z out? No, it's stuck. And because it's stuck, what we mean is it's actually stuck underneath still. So I rewrite it and I stick it underneath. Now if you'll remember back to my original problem, I only put this in the box. I need to drop this 3 down. I'm going to drop it down, and again, everything is just all multiplied. So now I just need to do the job of making things look nice now. 3 times 2 is 6, times 2 is 12, x squared, y squared, and then I have left over the square root of z. So as was mentioned last time, is just take it piece at a time. Break it down piece at a time, and you'll eventually get through it. Okay, that is the questions that came from the homework from last week, but we did have some questions that surfaced from the week before, so I'd like to look at those now. So the questions that came from the week before, let's start with this is coming from I think I may have gotten these out of order. I may have put these in the wrong place, so I'm not really sure where it's coming from now. But the question was on graphing inequalities. Because we talked a lot about graphing, but we didn't actually talk about, well, we kind of mentioned it a little bit. So we're going to graph inequalities. The first thing that you want to do is treat an inequality just like it's a regular line. So to graph 44 here, I'm going to treat this as y equals 2x minus 4. And graph that line first. So I'm going to plot my graph paper. I'm going to write my equation on here so you can see it. Now if you remember, this is actually written in the slope-intercept form. That means -4 has to be my intercept. So on my graph, I'm going to go to -4, and put a dot. My slope here is then 2. But I need a fraction in order to be a slope. So it'd be 2 over 1. So I'm going to go up 2 and over 1. And because I'm kind of crazy, I like to do it multiple times. Just so I can make sure that my line gets straight because, well, I just like to do it a lot. Now, what's really nice about graphing is you can also do the opposite. Instead of going up 2 and to the right, I can go down 2 and to the left. So I can go in the exact opposite direction too, and notice they all show up on the same line. I guess you didn't see that because it wasn't up. Okay, now let's go back to our inequality here. Notice that it says greater than or equal to. Because it says equal to, that means it can include everything on this line. Because it can include everything on this line, I want to make this line a solid line. If it had just been y is greater than, then I would write this as a dotted line. Because I want to include everything up to that line, but I don't want to actually include anything on the line. Now I need to pick what point I want to put in here. The best thing to do is to look at your graph and just simply pick an ordered pair to substitute in. What would probably be, looking at this graph, what would be a really good ordered pair to substitute in? Make it even easier than that. The origin. It's clearly not on my line, so let's put in the origin, or 0, 0. If I put in 0, 0, I end up with 0 is greater than or equal. 2 times 0 is 0 minus 4. And then you ask yourself, is that true? Is 0 greater than or equal to a negative 4? Yes. And because that's true, everything over here on the exact same side has to be a solution. And so we simply shade it in.
So you can make any point, not a point that has a dot on it. Or you say 0, 0
because it's an easy point. Okay, the question was you can pick any point as long as it doesn't have a dot on it. Yes. Pick any point that's not on this line, and any point will work. So if we had used 2, 0, we would have ended up with 0 is greater than or equal to, well, 2, 0 we wouldn't want to use because it's right on the line. But we could use 2, 1. And if we use 2, 1, we'd have 1 is greater than or equal to, when we do the work here, we get 0. And 1 is indeed greater than or equal to 0, so it would be everything over here. So you can use any. In fact, if you wanted to, you could even use an ordered pair from this side. What would happen if we picked an ordered pair from this side is we would get a false statement. And the false statement would tell us none of those can be the solution. It has to be the other side. So that's how you graph an inequality. Then we have a question on '54. 54 was writing an equation in standard form for each line. There are multiple ways in which you can do this. Probably one of the easiest ways to try to do this is to see if it crosses right at the intercept, the y-intercept, because if it crosses that y-axis at a nice number, then your job's a lot easier. This one appears to cross at the y-intercept. It appears to cross right here at -1. So, if we use -1 right here is our intercept, now we need to know our slope. So we go back, and what we're doing is we basically want to pick 2 points it crosses very nicely on. So we know it crosses here, and I'm going to massacre this because I've got a very large pen. And it crosses right here very nicely too. So what we want to do now is basically draw a triangle. How much up did we have to go, and how much over did we have to go? And we simply count. We're going to go up 1 unit and over 2 units. And that tells me my slope. Remember, slope is rise over run. So my slope here is going to be 1/2. Now I can put it into an equation. Y equals mx plus b. Plus the -1 is the same thing as subtract 1. But if you'll notice, this asks you to write it into standard form. So putting it in standard form is going to require a little more work. The first thing we're going to have to do is get rid of our fraction. So to get rid of our fraction, we're going to multiply everything by 2. So if I multiply the whole thing by 2, I get 2y equals 1x minus 2. And now I need to put my x and y on the same side. But if you recall, the x needs to be positive. So because of that, I'm going to make a series of choices. I'm going to move the 2y to the other side. And I'm going to move this 2 over here. So what I end up with is 2 equals x minus 2y. Now you could do that in multiple steps. I did it all in one step, but you can do it in multiple steps. Notice the 2y has now been moved. Over here I have x minus 2y. This 2 has now been moved over to here. Well, standard form, I simply switch them, and I get x minus 2y equals 2. Now I will tell you, this one does not match up with the answer in the answer key. And the reason is because it didn't actually cross nicely at -1 like it appeared to. It was off. I believe it was, the y-intercept was, I think it was 8/7, -8/7. So it was 1/7 off. That's very hard to tell on this little tiny piece of paper. And so most of you probably got this answer and then thought you were doing it incorrectly. But you are doing it correctly. It's just that it didn't actually cross as it appeared to. The same thing works with, if you look at question number 55, you'll notice that 55 doesn't actually reach the y-axis, so we're not quite sure where it crosses. That's okay, we can still write an equation. The way we write an equation here is we pick 2 ordered pairs. It does look like it crosses at -7, 0. And it does look like it crosses at, is it -3, 4? And so we can actually calculate it this way. Now I could calculate the slope here if I would like to, or I could simply count what the slope is on my graph. So going back to my graph, if I draw my triangle, it looks like I'm going up 4, and I'm going over, is it 4 also? I went on 1, 2, 3, 4. So my slope here would be 1. Because 4 over 4 is 1. Now, the way I would calculate it, if you recall back to our formula, is you subtract your y values, and you subtract your x values. So if I subtract those, I end up with 4 minus 0 over -3 minus -7. That becomes plus. And I end up with 4 over 4, which is 1. But I found that from the graph. Okay, but I'm not done yet because I know my slope, but I still need to write my equation. Well, if you remember, y equals mx plus b. I don't need the 1 there because 1x is the same thing as x. I have an ordered pair I can substitute in. And actually, I could pick either order pair. Pick the one that's going to be easier for you to do the calculations. I'm going to pick the one with 0 because I like 0. 0 is easy to multiply by. So if I substitute it in, this is my x value, this is my y value. I get 0 equals -7 plus b. Notice now I can solve this, and what does b equal? I get that by adding 7 to both sides. Now I can write my equation. Basically, I rewrite this, but instead I put the 7 there. So I've got y equals x plus 7. Is this in standard form? No. So to put it in standard form, I'm going to have to do a little arranging again. Again, I'm going to minus the y to the other side. And that's going to give me 0 equals x minus y plus 7. And now I need to minus the 7 to the other side. I could have done them in one step like I done the previous problem. And what I end up with is x minus y equals a negative 7. Okay. I had also been asked to show, I think it was problem 58. 58 follows the same format. So 58, you would follow the exact same format. So with the time that we have left, I think Hal would like to go over that. No? Yes?
Absolutely.
Okay.
We have a question from online.
Okay, now that I erased it, hopefully it wasn't about that one.
It's just, she says, why don't you subtract x from both sides?
Okay, so let's go back to,
Sorry, sometimes it takes me to type the question out.
let's see, what was it? X plus 7.
X plus 7.
Okay, I can actually subtract, thank you. I can actually subtract it. The question, by the way, for those of you in Adobe land is why didn't you just subtract x from both sides? You can actually subtract x from both sides. But when you do that, I get negative x plus y equals 7. Now in standard form, the leading coefficient here for the x, that needs to be positive. So I can subtract the x, but now I need to go ahead and multiply everything by negative 1. And doing that would then give me my leading coefficient there to be 1, positive. So yes, there are multiple ways to solve the problem. The key is just to know when enough is enough. And so here we need to have the x, the number in front of the x, the coefficient, be positive. And that's how we know we have it in standard form. Okay? Excellent question. Okay.
Here it is. Really, what we're looking at, and let me pull this down, and we'll show. So when we're looking at it, like Chantel diagram, we're looking at the probability of if we roll that first dice of, and let's take an even number. Let's do number 5. Let's do an even number and 3 because that looks like what she's got here. So we're saying, what's the probability if we roll the first dice is an even number and the second dice is a 3? And then we also need to look at the probability of what happens if the first dice is a 3 and the second dice is an even number. And you guys, I didn't do that because I got up here, I got nervous, and I got staged right. So anyway, you guys, I am so sorry. Man. Yeah, just don't tell any of my former students I made a mistake. I've never made any in the classroom. Ever. Okay, that's a lie. So let's just look at number 4 and the probability of 4 and 1. So really what we're going to do is we're going to look at the probability that the first dice is a 4 and the probability that the second dice is a 1. But then what else do we have to look at? We also have to add on to that maybe that first dice was a 1, but then what would that make that second dice? A 4. Okay, so if we do that, the probability that the first dice is a 4 is what? 1/6, right? And the probability, and I'm bringing my notes over by me so I don't mess up now. Yeah. The probability that the second dice is a 1 is what? 1/6. Now, I do have to add on to this other probability, because what happens if that first dice is a 1? So what's the probability that the first dice is a 1? 1/6. And what's the probability the second dice is a 4? 1/6. What's 1/6 times 1/6? 1/36. And again, 1/6 times 1/6? 1/36. What's 1/36 plus 1/36? 2/36, which gives us 1/18.
Success.
Yay.
That was creepy. Voice came out of nowhere. Okay, so number 5. And you guys, again, man, I can't believe I did that, but these, I know they look intimidating, and I made them look a lot more intimidating than they really are. And I do apologize for that, and we'll play around with some of these next time as well. But for the sake of time, we'll just do number 5, because we also want to talk about some factoring as well, right? You did already. Okay, fantastic. And you just talked about reverse flow. Very good. I was pouting. I didn't hear it. So, okay.
In your packet that's available online, there's a whole bunch of probability questions. Try those probability questions. Email us the ones you want to see next week. Remember, put Praxis in the title.
Yes.
And we will go ahead, and those will be the ones that we choose to look at next week.
Yep. And I'll hit those good and hard. And we'll also look at a lot of geometry next week as well. So, and you guys, once we're done with these classes, if you still have questions, please feel free to email. We'll get back to you. We'll answer the questions that we can answer. We're here to help you. We just want to make sure we're helping. So, okay. So back to number 5. So the probability of an even and a 3. So first we'll look at the probability of even and the probability of 3. But then what do we have to add on to that?
Probability of 3.
Okay. The probability that the first dice is a 3, and the probability that the second is an even. Okay. So what's the probability that the first dice is an even? 3 out of 6, right? 3 out of 6. How about that the second dice is a 3? 1 out of 6. Plus that the first dice is a 3? 1 out of 6. And the second dice is an even? 3 out of 6. So, what's 3/6 times 1/6? That would be 3/36, right? 1/6 times 3/6? 3/36. What's 3/36 plus 3/36? 6/36, which simplifies down to? Oh my goodness. Yeah, always go to class with your notes, you guys. Oh my gosh. I'm so embarrassed. Okay, we have time to do number 6. Do you guys want to look at number 6? Okay. Okay, number 6. The probability that a number is greater than 4, I'm just going to write greater than 4 and a 2. Okay, so first we will do what? Okay, greater than 4. Probability of greater than 4. And we're going to multiply that by what? What's our second dice going to have to be? A 2. Probability of 2. Plus, we got to add on to that. What's our first dice going to be? It's a 2, right? Probability of a 2. And the probability of Greater than 4. Okay, so what's the probability that we're going to roll that first dice greater than 4? 2/6, right? Because we've got a 5 and a 6 that are greater than 4, so 2/6.
So you don't count 4?
No, because it's not saying greater than or equal to 4, it's just saying greater than 4. Yep. So 2/6. What's the probability that we'll roll a 2? 1/6. Okay, what's the probability? So now we're adding this on. So what's the probability that we roll that first dice as a 2? 1/6. And what's the probability that we roll the second dice greater than 4? 2/6. Okay. 2/6 times 1/6 is 236. Plus, again, 1/6 times 2/6 is 236. What's 236 plus 236? 436. And that simplifies down to 1/9. Okay. So, man, I made that harder than it needed to be earlier, and I apologize, you guys. So, thank you for being patient with me, and I hope we have amnesia for next week and don't remember my mistakes. But, you guys, any questions that you have, please feel free to send them to us. And like I said, we've got one class left, but that doesn't mean that we're done. If you still have questions, if you're looking online and you're finding these resources that help you study for the Praxis, and you run into a problem and you just don't know how to do a question.
We have 2.
How many
Big class.
You have
Sorry,
two.
we have 2.
I'm sorry, 2 classes. So 2 classes left. So if you run into a problem, yeah, my bad, sorry guys. If you run into a problem, even after we're done with this, send me an email, send Chantel an email, ask, hey, how do we do this? We'll get back to you as soon as we can. If it's not a question that we can answer very easily in email, I may ask for a phone number and I'll give you a call or whatever we need to do. So, we're here to help you out. We want to make sure you guys are successful. So, thank you very much.
Have a good evening.
If you guys didn't get a chance to sign in when you came in, or the sheet was not there, make sure to sign in.